Last week we talked about thermal energy, and this week we're going to kind of continue on that and talk more about that. So I want to review real quick the three types of energy that you know from chemistry. The first one is potential energy, and you know that is stored energy. The second type would be kinetic energy, and you learned that before. Kinetic means movement or motion. Well, the one you just learned about last week is thermal energy, and so that's just measuring the kinetic energy as heat. And so one of the things we talked about before was temperature. The higher your temperature is, it means the more energy that's happening, the more kinetic energy that you have. The last definition we want to learn this week is enthalpy. And enthalpy is the change in the amount of heat that happens in a chemical reaction. And we use the symbol delta H. And so delta is this triangle right here. It means change of. So it's the change of heat in a chemical reaction. So there's two ways to measure heat. And the first one is joule. So just like seconds measure time, or grams measure mass, or liters measure volume, joules measure energy. So we use the symbol, the letter J, to abbreviate joule. Now sometimes you'll see kilojoules, and that's just 1 kilojoule is 1,000 joules. The other definition is calorie. Now the heat calorie is the heat required to raise the temperature of 1 gram of water by 1 degree. Now notice it does say water here. Calorie in this definition is specific to water in regards to the temperature, but we'll learn more about other substances and what's called their specific heats in a second here. Calorimetry is the measurement of heat, and it's just a way we can actually calculate how much heat is either absorbed or released in a chemical reaction. These are just two examples of devices called calorimeters that will help you measure that heat. If you take chemistry in college, you'll learn more about these and probably do a lab where you'll measure that. This right here is a formula that we use to measure heat, and it reads Q equals mc delta T. Q is equal to mass times specific heat times the change in temperature. Now this is not a formula that we're going to be calculating with this year, but if you do take AP chemistry or chemistry in college, you'll definitely use this formula. You'll even use it in physics whenever you learn about thermochemistry. Q stands for the heat in a reaction, so it's the unit we use is joules. M is your mass of substance, and it's in grams. So if you're given a mass for a problem and it's in kilograms, you would need to convert it to grams. C is specific heat capacity, and that stands for the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree. Earlier when we learned the definition for calorie, that was for water. Water's specific heat is 4.18 joules. It takes 4.18 joules to raise water, 1 gram of water, by 1 degree Celsius. All substances in chemistry have their own specific heat. That's why it says specific. And we can look those up on a chart. And then delta T is the change in temperature. It stands for temperature final minus temperature initial. If you know the mass, the specific heat, and the change in temperature, you can actually calculate how much heat was absorbed or released in a reaction. Now when we talk about absorb or release, there's two words that we're going to use. In the picture on the left, you can see that heat is escaping outwards. It's making the surrounding area warmer or hotter. This is called an exothermic reaction. Energy is released into the surroundings as heat. The temperature of the area outside of the chemical reaction would become hotter. If you stuck your hand near this beaker, you would actually feel warmth. You would feel the heat leaving the reaction, and it would go into the surroundings. On the right here, the difference is the temperature is decreasing in the surroundings because the chemical reaction is pulling the substance in. This is what we call an endothermic reaction. Energy is absorbed and the temperature of the surroundings are going to drop. If we look at a graph here for the change in heat in a reaction, this graph is an exothermic reaction. And so we can see over here on the left, on our y-axis, we're starting with energy, and then we have what's called our activation energy. this is the energy required to get the reaction started. At the end of the reaction down here, notice we finished lower than where we started. This is because heat was released, and so this is an exothermic reaction. When the graph finishes lower than it started, that's an exothermic reaction. Remember that word enthalpy we learned earlier? That was delta H. The delta H for this reaction is negative because it's decreasing. So the change in heat is a decrease in energy. Notice in the equation down here, we started with the reactants and then we finish with products and energy. This is an exothermic reaction. Delta H is always going to be negative for an exothermic reaction. Notice this graph for endothermic is different. It's opposite. It starts off low in the beginning, and then an endothermic reaction absorbs energy. And so we can actually see that it's gaining energy, and in the very end, it finishes with a higher amount of energy. Delta H is positive for this reaction, so the enthalpy is increasing in this reaction. Down here at the bottom, we notice that we start with reactants and we're adding our energy, we're absorbing it, and then we finish with our products. So two things to remember. Delta H is always negative for an exothermic reaction, and delta H is always positive for an endothermic reaction. We're going to work a few examples here to be able to identify, just based on a chemical equation, whether something is endothermic or exothermic. In the first reaction here, we're looking at methane plus oxygen yields carbon dioxide and water. Notice it doesn't give me anything about heat in the reaction, but over here to the right, we see delta H, and it says delta H is equal to negative 890 kilojoules. We just learned that which type of reaction is a negative change in heat. That would be exothermic. In this reaction, we have calcium hydroxide, and we're producing calcium oxide and water. Notice the delta H here is positive. So when it's positive, it's a positive change in heat. That's going to be endothermic. In the next two examples, they don't tell you the delta H off to the side of the reaction. Instead, they incorporate it within the equation. So notice in the third example, we have our two reactants, sulfur and oxygen, and we're producing sulfur trioxide plus heat. In this reaction, we're producing heat. So you have to think about the definitions. Which definition means to produce or to release heat? That would be exothermic. In the final reaction, we're taking heat and we're putting it into the reactants. So the reactants are absorbing that heat. We're putting it into the chemical reaction. And then we're finishing with a new product. So if it's absorbing the energy, that would be endothermic. Some of you may have seen this graph before. This is called a heating curve. And we've got different phases of water. So at the bottom here, below 0 degrees Celsius, water exists as ice. This would be the solid phase. Notice at 0 degrees, what happens to our temperature here? Temperature remains constant during a phase change. So the phase for a solid to liquid is not going to increase in temperature until every last molecule has shifted from the solid to the liquid phase. Once that happens, we keep increasing our temperature all the way up until water boils at 100 degrees Celsius. Notice temperature still remains constant. It's not going to increase until every last substance or every last molecule has changed into the gas phase. Whenever we absorb heat to go from ice to water or water to steam, that's an endothermic reaction. To melt water or to boil water, to melt ice or boil water, you have to add heat into the reaction. If you take heat away, that's an exothermic reaction. So we have to release heat from the substance to become cooler. So if we release heat from the gas phase, we'll condense back into water. And if we release that heat even more, that's when we freeze. So here we have a phase change diagram, and it's a little different in appearance than what we just looked at, but it's the same idea. It shows you different regions. We have solid on the left, we have liquid up here, and then we have gas on the right side. So by adding energy into the substances, if we increase temperature and increase that energy, that allows us to change from solid to liquid. That melts. Or we can go from liquid to gas, vaporize, or from solid to gas, sublimation. If we take heat away and remove that energy by decreasing the temperature, then we're going the other direction. That's how we freeze or condense or depose or deposit for deposition.